Hi there, I'm Regina. This is my presentation on Lab1 on constant velocity. For my presentation, for the first part, I will be talking about the introduction, and for the second half, I will be talking about the experiment details. The purpose of the lab was to observe motion of an object moving at a constant speed without it changing directions, and to create a computational model based off glow script and physics principles, otherwise known as Newton's second law or the momentum principle. And another thing that we had to do was to analyze the data given by the model and compare it to our data presented in Tracker. Related to models and fundamental physics principles, we have Newton's second law of motion, which states that the rate of change exerted on an object is equal to the magnitude and direction of the force inflicted on it. Then we have the velocity formula, which is distance over time, and F net is equal to 0. The change of momentum is equal to the net force acting on the system multiplied by the duration of the interaction. And for our next formula, we have delta P is equal to F net times delta T, which will later become R of F equal to Ri plus average velocity times delta T. During this lab, the model that was used was the orange ball rolling in a smooth straight line, and for this experiment, the system was the orange ball itself, and its surrounding was the ground, air, and anything else around it. Relating to the experiment summary, the methodology behind this was to roll the orange ball in a straight line, ensuring it's at a constant speed, and to record a video of this. Then to use the Tracker app to locate the position of the ball at various times. Then to analyze the position time graph of the orange ball. Then to use the computational model to input the ball's initial conditions. Then to analyze the predicted position time graph. Then lastly to compare and contrast both of these graphs. For reference, this was my experiment, which I will show. Preview of my results. Based off my computational model, the orange ball was moving at a constant velocity and pretty accurately followed the observed position. The average velocity of its predicted motion was slightly higher than the observed one, and observing the motion of the orange ball, it was moving at a constant velocity. In the previous slide, I briefly went over my results, but without further ado, here are all of the results and findings of my experiment. To start off, I found the mass of the orange ball, calculated the initial and final position, the time, and calculated initial velocity. Here you'll find the position results, and what this graph is showing is the results from the computational model and from the Tracker application that I used. As you'll see, the observed position followed the predicted path pretty closely, and towards the ball's path at the end you can see a slight deviation, but the deviation doesn't really start for a longer period of time until around 0.45 seconds. Here you'll see that this is the code that I used for the computational model, and in line 32 I edited the mass of the object, which ended up being 0.56 kilograms, and in lines 35 and 36 I edited the vector x position, and in line 40 to get this value for delta t I did 33 divided by 1,000. This was the rest of the code used for the computational model, and you'll see in lines 58 and 60 I updated the formulas used for the object's velocity and position. For the discussion portion, I want to touch on possible errors, one of them being when I rolled the ball, the ground could have been bumpy, which could have caused additional frictional force, which meant that the ball was at a non-constant velocity, or there could have been human error when I was tracking the center of the mass, which would have led to incorrect data points. Now, what if the x and y axes were switched? All this would mean is that my slope and velocity would be negative, speed would remain the same, And this just means that frictional force was not considered, so to say that the net force is equal to 0 isn't possible because we don't know how many pushes and pulls were actually added to get that net force of 0. In conclusion, when the orange ball was in motion, it stayed in motion, and for the most part, it did follow its predicted path, which means that the computational model was mostly accurate. Throughout this lab, I was able to understand Newton's second law to predict motion and velocity of an object.